Hello, scientists. Any idea what we're talking about today? All right, happy Friday. We are talking about the type of energy today that we call light. I want you to look at the pictures in this on the slide here of all the different types of light that there are. Look at the different sources. Remember, a source is where it starts. Look at the sources of light there. Some of those are called natural light, meaning that you can find them in nature, and others are artificial or made by humans. Do you see the little bug in the bottom left? Wait another month or so until the evenings outside stay warm, and you might get to see some of those guys flying around outside in the dark. You should see flashlight, candles, the sun, light bulb, lasers, fire, Christmas tree lights. And of course, since we're a school of the arts, I've got some nice spotlights here in the front for the stage. So what exactly is light energy? It's pretty easy. Light energy is literally light you can see. Easy peasy, right? Light energy can travel through space, which is something that sound energy cannot do. That's why we can see sunlight, but you actually can't hear sounds in space. Light is also absorbed, reflected, and refracted. We're going to learn more about those words today. All right, do you see the spotlight on my cute little teddy bear? How could you make the spotlight show up on something like that without actually shining the light directly on it? If we were in the classroom, I would be giving you some materials and giving you flashlights to let you try to do this. But I want you to think about it on your own and see if you think you could come up with a way of doing that. Anybody have an idea? All right. I'm going to show you a quick video of my kids helping demonstrate this and see if you had this idea as well. Hey guys. All right, so I showed you that picture of the spotlight shining on the teddy bear, and I figured we would try to show it. So I have my kids here. This is Jacob and Timena, and they're going to help me out. We've got a flashlight. We're going to try to get a nice spotlight on our adorable little teddy bear, but Timena is not allowed to shine the light at the teddy bear. We've got to shine it, point it somewhere else. How do you think we could do this?
I think if we use a mirror, the light will reflect off the mirror and we can point it at the teddy bear.
You want to try it? See if that works. That's a pretty good spotlight on that cute teddy bear. Or Celeste, my other daughter, said, very good. Let's try it with a laser. This is a laser pointer. If you look at the floor, hold on. If you look down at the floor, that's a laser light. Sometimes people have these for their dogs and cats because sometimes animals like to chase after them. Lasers are very, very intense beams of light. Guys, for safety, we never, ever, 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 ever point any kind of light at someone's face, especially a laser lighter. It could truly damage people's eyes. So we're going to be really careful. And we're going to try the same thing. And this time I want you to see if you can get the laser light on the bear's belly. You don't want to shine it in his face. So let's see if you can work together and get that light. So shine it at the mirror. Get it on the bear's belly. Hey, good job. All right. Do you think you can change it up and this time shine it on our lovely unicorn's belly? See if we can get it to shine on the unicorn belly. And there it is. Good work, guys. All right, thanks. All right. Did anybody else think about using a mirror to reflect the light onto something else? That's what we call reflection. Okay? So it kind of looked, this is a diagram of it, reflections at work. That's sort of what I had my kids doing. So the one boy has the flashlight shining at a mirror. And if you look at the light, it's going in a straight line, straight to the mirror. And then it's kind of almost bouncing off the mirror and straight at the other boy and right on his shirt. That's an example of light reflection. And that's a word you probably already know. You see a reflection every time you look in a mirror. It literally just means something bouncing off a surface. So bouncing or moving off of that surface and back out. We see things because the light bounces off whatever it is you're looking at and into your eyes. So really everything you see is because light bounces off. Some things, even like certain colors, reflect light better than others. Other surfaces, things like smooth and shiny, glass, water, polished metal, that will bounce light back at your eyes at the same angle. So it looks very straight and just like the original object. So if you look at that photo on the slide, the mountains and the trees show up really well in the water, and they look exactly like the real ones because of that reflection. And the water is very smooth and flat. So it's like a perfect reflection. If you look at the little picture over here, we have the sun shining, so that would be the source of the light, and the light hits the tree. And some of that light is reflected or bounces off the tree, kind of in all the different directions. And some of it ends up bouncing basically to your eyes, and that's why you can see a tree. So let's look what happens when light reflects off a surface that isn't quite as flat. It's still shiny, so it reflects well, but it's not so flat. Can you guys see those pictures? Look at our legs. That is my son Jacob and my mom and me. And there's Jacob again over here. Look at our legs. We were on vacation a few years ago and we went to a candy store and found some silly mirrors. And sometimes they have those kinds of mirrors in like a carnival or a fun house. We were literally laughing so hard. We had tears running down our faces, like we were crying. As we moved closer or farther from the mirrors, our arms and legs started getting really long and skinny or really short and fat, depending on which way we moved. Those kinds of mirrors are a lot of fun, and now you can kind of understand how they work. Remember, you see yourself because light shines on the mirror and it reflects back at your face. And it travels in that straight line. So when it hits a regular flat mirror, it bounces back straight, so you look normal. The silly mirrors, though, are curved. So the actual mirror is kind of curved like this. So it has a curved surface. And so the light hits the curves at different angles. Think about math when you were learning about angles. It hits it at different angles, and it bounces back that way or reflects. So that's why you end up looking really strange. Another word that you can use for how that is distorted. And distorted just means pulled or twisted out of shape. And I definitely think my legs look like they were pulled out of shape in this mirror. So there's another picture of some of those mirrors. You can see the curves better on those. So it just kind of bounces your reflection back to your eyes at different angles, which makes some parts of your body appear super short or long or thin or wide. Next time you come across one of those, maybe at a carnival or something one time, I want you to think about reflection of light and angles. Because I know when you go to a carnival, your favorite thing to do is think about math and science, right? These are some other examples of curved mirrors that we sometimes see. So this is the side view mirror of a car. And sometimes on the mirror, it actually has words printed on it. It says objects in mirror are closer than they appear. And the purpose of that is so a driver can look into that small mirror, but see a really big space. They can see pretty far back behind them. They can see way off to either side, which helps them see what's around them as they're driving without having to turn around. So that's safe. But they do have to remember that when they see a car in it, just like this car here, it's actually closer than what it looks like. So you got to be careful and not pull right in front of them. because they're a little closer than you think. This mirror is sometimes called a makeup mirror. People use that to look at places like on their faces up close, really small areas, because it magnifies it. It's curved enough that it makes your image appear bigger. So that's how that one works. This one is curved quite a bit. Sometimes you see it in a parking lot or when you're coming down a really small street and there's like walls on the sides and you can't see in one direction. It would be really dangerous for your car to pull into the street without being able to see if there's another car coming. And that mirror gives you a big angle so you can actually look down the road if you look up at the mirror. Sometimes stores use those mirrors as well so that the workers can look up at it and kind of see the whole store all at one time from up high. So they're very useful. All right, so we talked a lot about light reflecting and bouncing back. The opposite of reflecting is absorbing. Think about what a paper towel does when you spill water and you put the paper towel on it. It absorbs or soaks up the water. Well, light is an energy, and different surfaces can actually soak up or absorb some of that energy. Different types of materials may absorb or reflect light differently, and different colors also do that. They can change things. Light colors reflect more. So the lighter the color is, the more it bounces off and it reflects. The darker the color, the more light energy is absorbed into it. So a really good example is like in that picture, a very light colored sidewalk, and then the really dark black, what we call asphalt, the black pavement. And if you've ever walked outside barefoot on either of those types of surfaces in the summertime, when the sun is shining real bright, then you probably know what I'm getting ready to talk about. Both surfaces might get really hot, but the black one is going to get hotter. That's because black actually absorbs and soaks up the light and the heat more than the light-colored sidewalk does. And it actually traps that heat in it. And that's something people try to remember when they're building or making something different colors. Different colors do affect things differently. And you might say, but the grass is a darker color than the sidewalk, and it doesn't burn my feet like that. But you also have to think about it's a different kind of material. And that can affect it as well. So with that absorption or absorbing, think about these kids and their clothes. Which outfit do you think would be better for playing outside on a really hot, sunny day? And which one would you think would be better for on a cold, sunny day? Both very sunny. This doesn't really matter if you're in the house or it's not at all sunny, because we're talking about that light energy. But one of those is a lot better if it's actually hot outside already. Wearing a dark colored shirt outside in the winter helps your body soak up and keep more heat in it, which is good. If it's cold air outside, you want to kind of trap that sunlight and warm up in your shirt. If it's the summertime, you would stay cooler by wearing a very light colored shirt or clothing all over. So if you're going to be outside and it's sunny, think about the color of clothes you're wearing, because that can actually help make a decision about whether you're going to stay warmer or cooler. And that's in addition to the kind of material it is. Obviously, a hoodie is going to be warmer than a short sleeve t-shirt, but a dark blue hoodie is going to be warmer than a light yellow one, okay? Here's our next word. And for this, you guys get to do an activity on your own, okay? This is a cool word. This is refraction. Look at it. It looks a little close like reflection, but it's different. So to show this, we'll try an experiment. If you have these objects at home and you want to do this activity along with me, push pause on the video until you go get materials and then come back. No problem, just push pause. If not, you can just keep watching and you can watch me do it. So if you have a jar, you're going to fill it about half full with water. I guess I did mine a little bit more than that. Fill it about half full, and then put either a drinking straw, or I have a pencil, which I think most of you probably would have, and put the pencil in it. And I want you to lean down and look at it where your eyes are kind of at level with the water. Do you notice anything about how the pencil looks where it goes into the water? Doesn't it almost look like the pencil or the straw is broken? It's kind of crazy. That's refraction. It's an example of refraction, and that picture is really good. You can definitely see it well there. Remember I said that light energy travels in a straight line, but it travels at different speeds in different materials like air, water, or glass. If you've ever tried to walk or run in a big body of water like a swimming pool or the ocean, the lake, you know it's really hard to move very fast through water. Light doesn't go through water as fast as it goes through air either. So when it slows down, it actually changes the angle that the light continues through. So it changes the angle of how we see it. We could say that the light actually bends. And the definition of refraction is when light moves through one material and then into another, and it changes speed and direction. So it bends. Refraction is light bending. I bet you didn't know that light could bend like that. You can explore this a little bit more at home if you would like. You can draw a big kind of thick arrow on a piece of paper and take that paper and sort of slowly slide it behind your glass of water and look through the front. The arrow should actually look like it changes direction as it goes behind the glass. Because if you think about it, the light is now going through one side of the glass, then through the water, then through the other side of the glass, and then through the air to your eyes. It bends several times as it's doing that, so refracts. You can try it with different kinds of clear containers. You can use different thicknesses of the glasses. Those are all examples of that light bending. If you look at the man in this picture trying to spear a fish, he's got a sharp spear tool. And before people had fishing poles, this is how they used to catch fish. That red dashed line shows what he actually sees when he's looking down at the water. But the yellow line shows where the fish really is. You can tell this fish here is where it really actually is. But when he looks, the light, so he looks and it looks like it's straight ahead, but actually the light is bending, so it's kind of distorting it. Remember that word? And it changes angles where the water and the air touch, just like your pencil did. So if that man actually wants to catch that fish to eat for dinner, he needs to understand refraction and stick his spear in a slightly different place. You could try this with some containers of water or a bathtub. Sometimes if you put something down at the bottom, it isn't actually where it looks like it should be when you go to touch it. It's kind of weird. I want you to check out the adaptation on this really cool fish. Notice his eyes are still under the water, so the light is bending, and his lunch isn't actually where it seems to be sitting. Let's take a look at this.
This archer fish is a sharpshooter. The mangrove maze is its prime hunting ground, and to hunt here successfully, he's had to evolve some creative ways to kill. When jumping doesn't cut it, the archer fish turns into a submarine water pistol and can spit out a strong and accurate jet of water to dislodge insects from their lofty perch. With their tongue against the groove on the roof of their mouth, they form a tube and force water out by snapping shut their gills. They can direct the jet of water with the tip of their tongue, even taking into consideration the arc of the water bullet due to gravity. Ready, aim, and fire. These mangrove marksmen often form shooting parties and will steal each other's prey. The archerfish is one of a kind. No other fish on the planet uses a jet of water to hunt. Bullseye.
That fish literally has to change his aim based on where the insect really is and not just how it looks from under the water. It's pretty cool. That's a neat adaptation he's got. All right, one more thing kind of like this is making a penny disappear. And I would love for you to try this. This is a little tricky for me to do and show you on a video, so I would love for you to try it. See if you can get this to work. Watch this to see how it works. And the penny is gone. Oh, no, there it is. It almost looks like it's floating or on the side, but it's not. It's down in the bottom. I love that. See if you can put a penny in the bottom of, and you don't even have to use a clear jar. You could use some other kind of bowl. And as you move angles and you're trying to look at it, see if you can get it to completely disappear from your view. The reason that happens is refraction. Refraction is that light bending when it goes into another kind of material, like water. All right, Bill Nye is old, but his stuff's still pretty cool. So we got one more video with him showing this.
This magnifying glass is making my eye look big. Now, why is that? Well, please consider the following. When light enters something like air, water, glass, or plastic, it slows down a little. And when it slows down, it changes direction. See how one eye is lower than the other? See? Take a look at this. Here are 3 straight beams of light. When they go into the piece of plastic straight, they come out straight. But if the plastic is tilted, the beams of light get tilted. See, they change direction, so they come out this side offset. Now, what would happen if the piece of plastic didn't have straight sides, but had a curved side, like a magnifying glass? Well, the light would change direction, right? Because the surface of the plastic is curved, each beam of light enters the piece of plastic at a slightly different angle, and it changes direction a slightly different amount. Look, over here, the beams of light come together at a single point. This is called the focal point. Now, what about the magnifying glass? Well, suppose your eye were over here, and light from the room were bouncing off of your eye and going through the piece of plastic this way. Well, then, the small area at this end would be spread out over a large area on this side. Your eye would be magnified. Thanks for joining me on Consider the Following.
All right, so hopefully that showed you some of the refraction, some examples of that. If you have looked at my YouTube channel yet and has all the different videos I've made so far for science, my new picture on that YouTube channel is me holding, just like Bill and I did, a magnifying glass up to my eye. And because of the curved part of the glass on that, it bends the light, it refracts, and it makes my eye look bigger than it actually is. You'll have to check that out. All right, do you have X-ray vision? I know sometimes we hear about that with superheroes. Probably not, which is why you can't see through things that are opaque. Do you know that word? Take a look on this slide. 3 more words that go along with light and light energy and how we see things. So these are some science words that help describe whether or not light can actually pass through something. And if so, can we see objects on the other side of it? Can we see all the way through it? So the first word is transparent. You can see right through it with no problem. Most of the windows in your house are probably transparent, or in your car. Basically, that's like plain glass or air. If you can see me right now, you're seeing through the air from my camera to my face, and that means it's transparent. Light goes through it, and you can see things on the other side very clearly. Translucent, however, means that only light goes through it. I remember this because that has L in the middle. So L in translucent is for light, only light. Think about the textured kind of frosted windows that are in the bathrooms on our 4th grade hallway at school. If you don't turn the lights on in the bathrooms at school, you can still see inside because sunlight is coming in through that window. The light comes through just fine. But nobody can see through the window from outside or inside because it's got a texture to it. It's translucent. It's not transparent. It's translucent. And that's a good thing for a bathroom, of course. Sometimes churches have stained glass windows, and that's also usually translucent, which means the light can go through those windows, but you can't really clearly see things on the other side of them. It only lets the light through. Okay? Opaque is the last word. That's a pretty cool word. That basically describes most other objects that you can see. So nothing can go through that, not even light. A table would be a good example. You could shine a flashlight down onto a tabletop, and if you went on the floor underneath the table, you're not going to see that flashlight light shining through. That's because the table is opaque. So let's look at a few other examples of these and see if you can identify which one is which. Looking at those different pictures, which ones are transparent? Go ahead and point to the ones that are transparent. So hopefully you said the clear plastic wrap that you can put to cover food. You can see right through that. That's transparent. As is the drinking glass, you can see through it. It might refract the image a little bit, but you can see things through it. It's transparent. And then this side of the glass window is also transparent. You can see the trees outside pretty easily. All right, which ones are translucent? Remember, lucent, light. It only lets light go through. So the other side of this glass window has some kind of like film on it, and that allows the light to still pass through, but you can't see through it. Same with this this window. A lot of times we see the translucent windows in bathrooms because nobody really wants to see in a bathroom. All right, and that leaves opaque. A shirt like that is usually pretty opaque. Possibly a little translucent if you put a shirt right up or a flashlight right up to it, but it's mostly opaque. And then, of course, a brick wall, definitely opaque. All right, got it? Scientists, the best way to remember all this new information is to write it down or sketch some pictures. please don't skip this part, all right? Be smart learners. Finish off strong with the science lesson. You can copy mine down, or you can write or sketch in your own way, but putting something down on paper will help your brain remember it better. So pause the video, go grab some paper and pencil or some crayons, and take a few minutes to write this down and write down what you learned today. Okay? You may copy mine. I've got some pictures and some words on there. I've got our new vocabulary words here. But do this. Take a few minutes to copy it down to help your brain remember it. All right, that's everything for today. I know it was a ton of new information, but it's good stuff. And we've officially finished our energy unit. So if you would like to re-watch this, by all means, please do. You can definitely even go on my YouTube channel and go back and look at old videos. You can re-watch them to keep it fresh in your mind. You can check out some of the read-alouds that will be there. Next week, we're going to jump into earth science. So that'll be the last science unit for the school year. And we're going to start with our planet Earth and its position in space. Some of it might be a little bit of a review from 3rd grade, but there's going to be a lot of new stuff too. Hope you have an awesome weekend, everybody. Love you and miss you. Bye.